Hello from Southampton. We came here to understand the present and future of one of the silicon photonic foundries that is leading manufacturing of advanced silicon photonics in Europe and the world, Cornerstone. I'm here with one of the leads, Callum. Thank you very much for having us. It's great to be in Southampton. What are you going to show us?
Well, we're going to show you around our clean room facilities where the prototyping services happen. Right here we've got a new e-beam system that was installed just last year. This enables us to mimic the high volume production in terms of resolution, but most of the work we do is based on DUV lithography.
Before we go to see all the facilities, how would you define Cornerstone as different from the other silicon photonic fabs?
Well, firstly, it's open source, so everything's easy to access. That makes it available to anybody. Secondly, we're very flexible. So many founders have fixed processes, which is great for volume, but we work at the prototyping stages where you might want to try something different. And that's what you can do with us, but it's in a scalable manner, so hence the deep UV lithography. Also, we have many different platforms, so we don't just work in the standard materials. We have platforms for, say, mid-infrared sensing, where we have suspended silicon or germanium on silicon.
So you can access suspended silicon already from...
That's right, yeah.
Wow,
we have a multi-project wafer service for that happens roughly twice a year.
So how long in wavelengths can you go with a suspended silicon waveguide?
About 7 microns, because that's when silicon itself becomes absorbing. But beyond that, we have another platform, germanium on silicon, where we can go to about 14.
Oh, wow.
So, you know, many gases and biological samples have strong absorption at these wavelengths, as you know.
So you have silicon photonics and you also have silicon nitride now.
Exactly, yeah. So we can support visible wavelengths for things like ion trapping, other biosensors, but also telecoms, of course. So
from 400 nanometers to 10 plus microns.
Indeed,
fantastic.
We cover the whole range. So that's why we're unique.
Let's see your toys now.
Come on in, let's go have a look.
So when we walk to the clean room, what are you going to show us now?
So we're basically going to be showing you the main clean rooms. And the main clean rooms are divided into the most silicon-based ones, where most of the users, PhD students, and the enterprise people are working with. And on the left-hand side, you're coming up, you'll be able to see the lithography side, which is the yellow room. And you'll see why it's a yellow room. It's quite bathed in yellow.
How does it work here? Because on one hand, you have students, researchers doing the research, and on the other hand, you're providing services to industry.
Yeah.
How do you combine these two activities?
I think it's so the research that's being done, and it also takes into account like different materials that are a bit more exotic, for example, and compared to like enterprise that we're doing focusing more on materials like the silicon, which is quite a controlled process. So the tools that are within the clean room, there's a wide range of tools that are being used as well, like the plasma processing tools. They are capable of handling like the exotic materials as well as the materials that are more controlled, like silicon. So the processing can be a little bit tricky from time to time, but I think we've got it down to like trial and error of like how do we control the process that even though we put a wafer in and it's not being affected by all these other exotic materials that has been done through research.
What's here behind me?
So the yellow room is where most of the lithography is done. So if you can see the little tool in the center there, that's a contact aligner. So that's when you put in like a contact mask and the mask sits directly on top of the wafer and then it's exposed. So the yellow light is mostly because of the chemical that's being spun on top of the wafer. It's photoreactive. So, but under the yellow light is neutral. And that's when you do most of your patterning before you take your wafers out to, before you develop the wafers to get the features that you want and then bring it over to the other side, which you will see later on for etching or any deposition.
I cannot see any of the wafers here. What is the current wafer size?
The current wafer size. So within our clean room, we do down from sample sizes, so really small, to whatever size you want, up to 8-inch.
So Callum, what are we looking at now?
So this is our planar clean rooms where a lot of the silicon photonics work happens. Like Hanuushah just told you, everything in here is capable of doing 8-inch wafers, which is the standard we use in Cornerstone. But anyone can access these facilities. So the university, other students and staff access it, but also we enable companies to come and put their own staff and use these facilities for their own commercial needs. So it's a very open facility. And that's what we're trying to do in Cornerstone, make everything easy to access.
Yeah, sure. You've recently been funded for the Cornerstone Photonic Innovation Centre. Tell us how that has changed Cornerstone, because Cornerstone's been around since 2014, helping academics primarily
Yeah.
prototype the materials. What is C-PIC offering that's different?
Sure. So the Foundry is still core to everything we do, but we'll be launching support programs for startups. So we want to help researchers get their work into the real world, and they need training for that because most of those come out of a PhD and an academic background. So we're putting programs together to help people understand what it takes to start a company. We're connecting with the accelerator programs such as Silicon Catalyst. We've actually got an on-campus startup accelerator here called Future Worlds, and we've embedded people in their team to support that. We'll be running far more networking events, and maybe we can have some partnerships on that type of thing. Training, we actually run a course where you can spend 2 days in the facility and see for yourself. You start with a blank wafer and you go home with a functional silicon photonics chip. So if you're a designer and you spend your life sat in front of a PC and everything's perfect in your simulations, you can come in here, see how it works, and then get a real grasp for what the challenges are in fabrication, and ultimately hopefully make better designs as a result of that.
Great. So if you're a company, for example, with an idea, do you have to have an advanced idea, or can it just be something a bit speculative? Can you come to Cornerstone with that?
It can be anything, yeah, speculative. And if you want to change a part of the process, that's something that we enable. That's core to what we stand for, right? Being flexible and open. So it doesn't mean that here's our standard process, take it or leave it. You might want to change certain parameters because you can make your device 10 times better. Come to us and we can help you do that.
So, Qingzhao, we're now working towards the deep UV tools that you have. You've shown us already the e-beam tools,
Yep.
But you're the only facility that has a deep UV tool. Why do you need that to scale up manufacture for companies?
It's because of most of the fabs, they actually only have e-beam tools. They do not have the DUV scanners. And in the industry, in most of the production site, they have this the similar type of the tool, not exactly the same model. So it actually helps for the small companies to get used to how these production site works, and then using the same technology, they will have a very smooth streamline to the actual production site.
So what are we looking at through the window?
We're now looking at the what's called scanner suite. So it actually consists of a Tokyo Electron track, which is an automatic wafer processing tool. It does the spin coatings to the bakings, and then it passes the wafer to the scanner. Once we have the exposure down, the wafer will return to the tool to do the development, post-exposure baking and development. This is all done automatically, which eliminates all the possible man errors, like you have a further, if you have a longer develop time or something. So it's a very precise control to make sure that all the wafers coming from the tools is highly repeatable.
So Callum, you mentioned training. There's a 2-day training that you offer that people go away with a chip. Can you tell us a bit more about that? What the options are and how people get in touch with you?
Yeah, sure. So we walk you through the full silicon photonics process. So you spend an hour on the deep UV lithography system, see how that works. Then we do an etching process, a cleaning process, a metallization. Visit our website. You can find more information about the course, but we're also part of a larger program called PIC Bootcamp. And in that course, it's more in depth. So you spend some time learning about design with some of our partners. Then you come here to see how to fabricate things. We then actually go to Bay Photonics in Torbay to do packaging. So through that program, you can start as a beginner designer, learn how to do design, learn how to make things, learn how to package them, and then you take home a fully packaged chip at the end of it.
Fantastic. And who are the other partners involved in the project?
So that's the University of Bristol, Light Trace Photonics, Wave Photonics. These are all UK companies, and Bay Photonics who do the packaging.
So Callum, you mentioned all the partners involved in these things are UK companies, but it's not only UK companies that can access C-PIC, right?
That's right. Yeah, we're open to the world effectively. We've sent chips to 24 different countries. We have over 100 users of our services, and many of them are actually companies. So people come to us when they want something a little bit different to what one of the bigger foundries offers, or perhaps because they're not yet ready for the volumes required to pique the interest of the major foundries. Now we're having a look at our testing facilities. Yeah, so here we have our 8-inch automated test facility. This does optical testing. So we run this mid-process flow to check the performance as we go through. We also then validate the component performance at the end of the fabrication process to ensure that we meet the spec that's required for our users. It actually enables electro-optic measurements. So whilst we have optical fiber in and out on the left and right, behind there's an electrical probe. So this is so we can drive heaters for tuning. And in fact, we've developed technology here at the university that enables permanent tuning of components. So take a ring resonator, for example, very sensitive to fabrication tolerances. Using technology developed here, we can permanently fix those errors. We have PDK where this is all open source. It's compatible with the packaging houses. It's compatible with our test facilities. So it's just things like where do you put your input and output couplers, but that's all standardized in the PDK. We've got support from the team to help if anybody has questions or they want to change things.
One of the favorite companies that we have in Optica is Ficontech, and I can see that for many years you had done great things. I remember a few years ago we had the erasable gratings in the silicon photonics, and now what we're doing here is being able to tune active elements in silicon photonics. How is partnering with companies like Ficontech helping the future of Cornerstone?
Absolutely, very good question. So really it's such an enabler because we're able to work on wafer level and automate. So it reduces the manual errors, the human errors, and it's all an 8-inch wafer. So it's not chip by chip, and that completely helps streamline the whole process now. So working with companies like Ficontech is a huge enabler.
Ramsey, in our previous meeting, in the private meeting that we had, we walked through different of your customers. Many of them are in cutting-edge applications in the, for example, quantum world. You're offering here characterization testing for all the applications. How do you work with these cutting-edge application demands?
So what we do is we kind of here the testing would be kind of application independent. So it would be kind of to test the wafer and how it performs. But then what we do is our PDKs and our technology platforms would be application dependent. So if somebody needs quantum, they would want a platform that has low loss on it, that matches their needs. Somebody who wants active functions may need SOI that's an active with implantation in it. So somebody working on healthcare or biosensing, then a germanium on silicon platform with a large kind of transparency range would be very good for them there.
So you can guide your customers and advise them in which platform they need. Can you also advise them how to design their chip for that platform?
All right, so there's specialized design houses, and we would recommend that people work with them, like Photonics, VLC, VPI. So there's a whole range of them, and they're really good at what they do. So we wouldn't want to try to replicate that. We would direct customers towards those places.
A few years ago, when Graham Reed invented silicon photonics, at least we could not imagine the explosion of this market. However, today we can see that companies like Global Foundries or TSMC are offering silicon photonics technology. How does Cornerstone fit into the puzzle?
Yes, so we would be a prototyper. We kind of help those that are wanting to try something out and then enable them to go to the scale up to where TSMC is. It would do the scale up for them. Global Foundries, we would prototype for the startup. So startups coming to us and they want to try out an idea. They want to show to their investors. This is the rapid prototyping house for them where they can get things done very quickly and try out an idea quickly to get investment in again.
We're about to meet Graham Reed. Can you walk with me there?
Let's go.
Callum, I'm really excited about the long wavelengths. We have been for many years thinking about photonic integrated circuits being the right technology for 1550. Then later on, people were looking at the visible with silicon nitride. But I think there is a really big niche for using it for longer wavelengths for many different applications, but especially spectroscopy. What's your vision for a silicon photonic structure that can transmit longer wavelengths?
Yeah, great question. I absolutely agree. I think there are huge markets for silicon photonics at mid-IR, particularly sensing, because you can imagine if we can make low-cost sensors in silicon photonics, that opens up mass markets like imagine a chip in every doctor's surgery and research work that's going on at the university here. By the way, we're very lucky to be part of a big research group. That's something different about Cornerstone as well. We think, we don't yet have the data, but we think we can detect early signs of cancer on a chip. So that could go into every doctor's surgery in the world.
In silicon and insulator, we always had the problem that the silicon oxide layer was absorbing the longer wavelengths. You managed to remove it and put it in a standardized process with a decent yield.
Indeed, yeah.
What's your secret?
The secret is to have a great team of people. And we have a legacy in this area from the research group that we're part of here at the university. So the detail is that we undercut the buried oxide layer, so we form suspended waveguides.
But you have a waveguide floating in the air. How is that reliable?
Well, it turns out it is. It's not that different to a MEMS system, right? So it's got lateral supports in silicon. We etched holes through and put it in HF, so that removes the buried oxide underneath. It's kind of like a little suspension bridge, but they are actually very stable. We post them around the world. They don't fall apart. We've even managed to get graphene on top of them and things like that, so we can make sensors or detectors for the longer wavelengths, because there are still many challenges, right, for mid-IR. The lasers are still very immature, detectors are very challenging, so we've got research activity.
One of the biggest challenges that we have actually in mid-IR is to integrate a quantum cascade laser on silicon photonics. Is there anything that you're working on that respect?
Yes, we have research programs in that area. We have a program called Mission. It's working on exactly that. We work with other partners in the UK, Sheffield. We've managed to get some mid-IR lasers, die, integrated to...
when are we going to have a silicon-based QCL in the market?
Keep your eyes on the website.
Hi, I'm Jose. Really nice to meet you. I'm really excited to be here. We are hearing about the activities in mid-infrared technology related to silicon photonics at Cornerstone. What can you show us?
So currently, if you look at here, is our germanium on silicon chip. And
this germanium on silicon, what wavelength are you using?
So currently we are using for the Phantom range around 5.6 to 5.8
micrometers.
Yes, micrometers.
Is this germanium on silicon extraction manufactured here at Cornerstone?
Yes.
How do you interact? So you are doing the characterization of the chip?
Yes.
How do you interact with the people who are actually fabricating the chip?
So normally we just for that, we normally just, do some design. We do our own design first, and then we actually have like a circle. We submit our job to Cornerstone, then Cornerstone fabricate the chip for us. Then we just do characterization ourselves. Then we just give them the feedback. Then we just keep...
To characterize these wavelengths, you need a laser at that wavelength.
Yes.
Are you using quantum cascade lasers?
Yes, we are using, currently, if you look at there, so we are using daylight solutions.
Yes. Optica corporate member daylight solution for the laser and for the detector. Also Optica corporate member all the way from beautiful Poland, Vigo Photonics.
Yes, Vigo Photonics,
I am so impressed with what you guys are doing, but mostly what I'm impressed is that you can offer this technology already to many other companies for them to do business in silicon photonics in the mid-infrared. Thank you so much for the nice demonstration. It is great to be here. Congratulations on everything you're achieving. Thank you. Bye-bye. Let's go to see more things.
We're now heading to Future Worlds. It's an on-campus startup accelerator here at the university. We've actually partnered with them in the Photonics Innovation Center because our mission is to help researchers get their research into the real world. And we're experts in the fabrication. We're not experts in starting companies, so we partnered with the experts. We can do things like help them to understand what it takes to start a company. How do you pitch to investors? How do you understand the market? They know.
And look who we have here.
Here's the boss.
Professor Graham Reed.
Oh, I didn't know you were recording.
Great to see you today.
Hello.
So we just saw the clean room. We were fascinated not only about the fact that you have extremely, well, very impressive, perhaps the best in Europe, even lithography. We saw the deep UV. I was extremely impressed with the long wavelengths. You can actually undercut the insulator layer and even go to 7 micrometers, and you have germanium and silicon. What's your vision? What's the future of Cornerstone?
Well, the future of Cornerstone is to support all of our users to maximize their ability to commercialize silicon photonics. But in terms of specifically what you were talking about in long wavelengths, the germanium on silicon actually enables you to go right out to 14 microns. Yeah. And so there are lots of environmental and healthcare applications, emerging applications, that can actually really transform some of the areas. You know, for example, we're working on whether we can detect cancer on chip, for example. Now, if you can do that, that means you could deploy one of those chips in every doctor's surgery, let's say, in every hospital. You know, you avoid the need for a lot of invasive biopsies, perhaps. Mm-hmm. Now, I can't tell you right now we can do it, but this is research that we're working on. And so these are game-changing applications, and environmental sensing is another one of those, and that's one of those long wavelength possibilities.
When you invented silicon photonics, could you predict that at this year we will have like TSMC, global foundries making production or real products based on silicon photonics?
Thank you for saying I invented silicon photonics.
Well, that's my personal opinion. You can quote me on that.
Okay, thank you. Well, look, I don't think at that time any of us could foresee what silicon photonics would become. You know, I was glad to just get some funding back in those days. But it's fantastic to see the opportunities that it now offers people. So, you know, obviously the support of the big foundries is going to transform some of the applications even in electronics. But what I really like is I think about the young people coming through today, the students, the early career researchers. They have so many opportunities to find a really valuable career in silicon photonics. So that's what I think is one of the important things going forward.
In the current landscape with the semiconductor fabs like Tower, like TSMC, like Global, talking about silicon photonics, where does Cornerstone fit into the puzzle?
Okay, I think Cornerstone has a very unique position, and especially in the UK. Now, we've been developing Cornerstone for many years, and one of the statistics is that last year we had more industry users than academic, despite the fact that Cornerstone was really started as an academic activity. And I think one of the reasons for that is that we can support some of the small companies to get to a position where they can have, a reliable prototype so that they can choose which foundry to scale up to. If they try and go to a foundry too early, A, they may not be able to get into a foundry at all. But secondly, they may lock themselves into the wrong foundry that doesn't really suit their technology. Yeah. So what Cornerstone can do is offer a prototyping journey without encumbering their intellectual property, without locking them in, to enable them to make a much more informed decision on the best way for them to scale up their technology.
And the students play a big role in Cornerstone. How are you attracting the talent? How are you dealing with the fact that photonics now is so cool and so demanding from every part of the world?
Well, in short, it is difficult. I think the reputation of the ORC and Cornerstone, and indeed our research group, helps. So people do want to come and work in the group. But, there is such a buoyant silicon photonics community out there that we're all looking and competing for the best people. So I think we have to face that in a number of ways. Obviously, we want the best people, and so the more we can do to attract them, the better. But perhaps more importantly, what the community can do collectively is improve the training, improve the support at earlier stages, get into the schools to describe what the technology can do for people. And we can't do that on our own. We have to do that as a community.
And now, when we were all like really excited about silicon photonics globally, everything was going really well. Suddenly, AI comes, and we see companies like Light Matter, like Celestial AI, one of your customers, Finchetto, making a really big push to the silicon photonics foundries, while we have companies like NVIDIA saying that photonics could be still too expensive for doing the right to the GPU interconnect. How are we going to address that huge demand that we were, at least myself, surprised to receive so early?
Yeah, I mean, obviously it's a very, very fast-moving field. I think maybe the way to look at that is that photonics can enable certain ways of doing calculations for AI. And there are niche technologies that are better for certain aspects of any technology, and AI is no different in that regard. So parallel processing of photonics gives opportunities for enhancing certain types of computation and calculation and so on. But actually there is another aspect of AI that's very important for photonics. So I mentioned that application where we're trying to look at cancer detection. Well, AI can move on the interrogation of those sorts of sensors. So it's not just about photonics supporting the hardware. The AI interrogation of vast amounts of data can vastly improve, well, lots of applications, not just photonic applications. But that's something that can enable photonics to really make even more impact. So there are many aspects to your question. We perhaps should spend longer, but I think that's the shortest answer I can give you.
One final question before we go for lunch. Right now, we're also very, very unprepared for the current geopolitical situation. We had the CHIPS Act in the United States. We had the European investment of 500 million for a photonics pilot line. We had the fact that some of the governments want to have their own supply chain on silicon photonics. How does the UK see this, as an opportunity or as a challenge?
Yes, good question.
Easy questions are not for you, it's for them.
Well, I think, we're in a position where we have a relatively new government. They have a lot of challenges, and so they're trying to get to grips with priorities. So I think the best thing we can do to support that is to demonstrate the opportunities available in photonics right across the board. I mean, the ORC has very broad-ranging technologies in silicon photonics, but also in other areas of photonics. And so we can make big contributions to the progress of photonics. If we talk specifically about CHIPS Act, and it really comes down to a lot of the work we do on chip fabrication, that type of thing. And again, making that contribution visible and available and understandable, I think enables the politicians to understand what we do and hopefully eases their decisions.
Great, it was great talking to you again, and thank you so much for having us here at Southampton. Thank you.
It's a pleasure. Glad to see you here. Thanks very much.
Let's go back to the train station.